All right, class, in this lesson, we are going to learn to identify some of the key features of the graph of a quadratic parent function. So let's go ahead and get started with example number 1. So the most basic quadratic function is going to be f of x is equal to x squared. Okay, so that is basically the foundation of all quadratic functions. So let's go ahead and plot some points and see what this function looks like. So first, I've got x values down this column, and these are my input values. Okay, so what that means is I'm going to take each of these x values and I'm going to plug them in for x, and the result of that will be our output, or f of x. Okay, so first, if we plug in -2 for x, we see that -2 squared is going to be 4. And so my coordinate there is going to be -2, 4. And then the next input value is going to be -1, and -1 squared is 1. And so we put the value of f of x as 1, and my coordinate here is going to be -1, 1. Okay, the third input here is going to be 0, and 0 squared in this function is going to be 0. So we're going to put the value of 0 there, and the coordinate here is going to be 0, 0. Okay, so just to be clear, the coordinate x, y is going to be this value, this value. Okay, going on to the next one, if we enter the value of 1 into this function, 1 squared gives us 1. And so the coordinate here is going to be 1, 1. And then lastly, we have the input of 2, and we put in 2 for x. 2 squared is going to be 4. Okay, so that's going to be 2, 4. Now, let's go ahead and plot these. So -2, 4 is going to be -2 on the x-axis, so -1, -2, and then going up 4, 1, 2, 3, 4. We're going to plot a point there. Okay, and then the next point is going to be -1, 1, and so we're going to go -1 on the x, and then +1 on the y, and so we're going to plot a point there as well. So the point there, and then we have 0, 0, so that's going to be on the origin, so we plot a point there on the origin. And then the next point would be 1, 1, so that's 1 on the x and then 1 on the y, and so we plot a point there. And lastly, we have 2, 4. Okay, so we're going to go 2 on the x-axis and then 4 on the y, along the y. And as you will notice, these points here are exact opposite or reflection of these points. Okay, these are equidistant from the y-axis, and so we would say that the axis of symmetry is right here, is our y-axis, or what we will call x equals 0. So if we go ahead and plot these points, okay, it will look something like this. And there's our parabola, and that's what our parent function will look like. I'm going to put these arrows to indicate that the function continues on into infinity in that direction. Okay, so that's the parent function. So let's take a look at example number 2. Example number 2 is trying to figure out how the value of the leading coefficient, okay, so this is the leading coefficient, it's the number before the x squared. We want to know how that affects the graph. Okay, what happens when these values are different? So let's take a look. We're going to put in the same f of x values. We already calculated these in the previous example, so we're going to go ahead and put those in. This was 4, 1, 0, 1, 4. Okay, and let's go ahead and start with these, with this column here. So this column is going to be double the values of this column. Okay, double the value of that column. So that's going to be 8, 2, 0, 2, 8. And then this column here is going to be half the value of this column. Okay, so half of that value is going to give us 2, 1/2, 0, 1/2, 2. Okay, so let's go ahead and plot those. I'm going to start plotting the blue first, and so that's going to be -2, 2. That gives us a point here. -1, 1/2, which is here. 0, 0, 1, 1/2, and then 2, 2. Okay, so that gives us a parabola that looks something like this. Okay, and then we'll go ahead and plot the black ones, the middle column, and that's going to be very similar to what we graphed in the first example. So we're going to have -2, 4, -1, 1, which puts us here, 0, 0, 1, 1, and 2, 4. Okay, so if we were to graph this, connect the dots, we get a parabola that looks something like this. And then lastly, if we were to plot the green ones, we would get -2, 8, -1, 2, 0, 0, 1, 2, and 2, 8. Okay, so it will look something like this. All right, so then what do we notice here? Okay, let's compare the green and the black and the blue. Okay, and let's take a look at the coefficients. So as the coefficients increase, right, this is 1/2, then this is 1, and then this is 2. So as the coefficients increase, we see that the parabola going from blue to green gets thinner, right? It gets narrower. So we can conclude that as the coefficient increases, the parabola gets narrower and narrower. And then the opposite is also true. If the coefficient gets smaller and smaller, then the parabola gets wider and wider. Okay, so what we have concluded here is that the leading coefficient will determine the thinness or the wideness of the parabola. Okay, so that is example 2. So let's go ahead and go on to example 3. Example 3, or in this case 2b, is to figure out how the sign of the coefficient affects the graph of f of x is equal to ax squared. Okay, how does the sign change? So if we were to plug in these values of -2, -1, 0, 1, and 2 into this function, we would get normally excuse me here, let's go ahead and type in black, it would be 4, 1, 0, 1, 4, just like in the first example. Okay, however, the function tells us to negate the values. Okay, so we're going to do that. We're going to negate these. Oops, 0 is still 0, -1 and -4. So then what we end up having is the following coordinates: -2, -4, -1, -1, 0, 0, 1, -1, and then 2, -4. And if we were to plot these, we would plot this point: -2, -4, -1, 1, 0, 0, 1, -1, and 2, -4. Okay, and if we were to connect these dots, we'd see that the function looks like this. All right, there we go. So there's our function. So what can we conclude? Well, when we put a negative sign in front of the function, right? So if a is negative, then we know that the parabola is going to be upside down or face downwards. Okay, so that is the effect of a negative sign. All right, let's move on to example 3. So now here we're going to be interpreting the quadratic function from a table. So no graphing, okay, just coordinates here. So here's the question. Over what interval is the function f of x equals 4x squared increasing, and over what interval is it decreasing? Okay, so in this case, we want to look down the y values, okay, the y values. And we're going to go from the smallest input, which is -2, and we're going to keep moving towards the largest input, okay? So we're going to move in this direction. So as we move in this direction, we see that this y value goes from 16 to 4 to 0, okay? 16 to 4 to 0. So over this interval, we see that this is decreasing, okay? Okay, over the interval, -2 to 0, we see that this is decreasing. Okay, so we're going to say decreasing over the interval. And even though we have this as -2, okay, it doesn't necessarily start there. This function actually goes into negative infinity. So we would say it would be over the interval -infinity to 0. We put parentheses around here. And then continuing on, we see that going from 0 to 4 to 16, we see that it's increasing. Okay, so over this interval, it is increasing. So we would say that this is increasing over the interval 0 to infinity. Okay. All right, moving on to the next example, example 4. So let's go ahead and apply the use of quadratic function in a real-life scenario. So here we have an example where an owner of a new dance studio is installing wooden floors in all of the dance rooms. And the question here is, how much should the owner expect to spend on flooring for a square room with 15 side lengths? Okay, so in this example, we see that this room is 15 by 15, okay, 15 by 15, and we are also told that the flooring is going to be $8.75 per square foot. Okay, so how do we calculate this? Well, the area of the room is 15 by 15, right? 15 feet by 15 feet. Let me go ahead and rewrite that as 15 feet by 15 feet. Okay, so that area then becomes 225 feet squared. So 225 feet squared, or 225 square feet. Okay, this also tells us that this is going to be $8.75 per square feet. So then I would say that the total cost is equal to the area, okay, or area would be x squared, or let me rewrite this. It would be x times x, right? So this would be the length and width of the room, which is x times x, times the cost per square foot of flooring, okay? And since we calculated the area as 225, then my total cost is going to be 225 times $8.75. And if we were to punch those into a calculator, we would find that that amount is $1,968.75. Okay, so that would be the cost of installing flooring just for the material in a 15 by 15 foot at a cost of $8.75 per square foot. Okay, last example. Here we are asked to compare the rate of change. Here we have a function where the a function of f of x, which is equal to 0.75 x squared, and g of x is equal to 1.5 x squared. Okay, so if you recall from an earlier example, okay, if the coefficient here is smaller, right, this coefficient is smaller than this one. So if the coefficient is smaller, that means that the function is going to be wider. So between these two, we would say that this function is our f of x, and therefore this function is our g of x. Okay, so we're looking at the rate of change over the interval 2 to 4, okay, where x is greater than 2, greater than or equal to 2, and less than or equal to 4. So what we're looking for is the interval from 2 to 4. Okay, so the interval from 2 to 4 equates to this point here and this point here as well. That's for f of x, and then for g of x, it would equate to this point here and this point here. Okay, now the rate of change, m, let me do this in a different color, m, which is our slope, which is also the same as the rate of change, is calculated as y2 minus y1 over x2 minus x1. Okay, so then let's take a look at what the slope of f of x is. So I'm going to do this in red. Okay, so now we're going to identify y2 minus y1. So in this case, it doesn't matter which one you identify as y2 or y1, as long as you maintain the same direction. Meaning, if I choose this as my y2, then I need to make sure that this is my x2. And if I choose this as my y1, this needs to be my x1. Okay, so we're going to take y2 minus y1, so that's going to be 12 minus 3 divided by x2 minus x1. So that's going to be 4 minus 2. And this comes out to 9 over 2. And that is our slope for f of x. Now we're going to do the same thing for g of x. And for g of x, we're going to take y2 minus y1. So that's going to be 24 minus 6 divided by x2 minus x1. So that's going to be 4 minus 2. And this simplifies to 18 over 2, which further simplifies to 9. Okay, so in comparing the slopes, we see that the slope of g of x, which is in the blue, is larger than the slope of f of x, which is 9 halves. Okay, and that makes sense. From here to here, this slope is steeper than from here to here. Okay, so what we've noticed is that when the coefficient gets smaller and smaller, right? So this compared to this is smaller. So as it gets smaller, the slope gets steeper. I'm sorry, the other way around. As the coefficient gets smaller and smaller, that's going from here to here. My f of x gets wider and wider, and so my slope is not as steep as that of the blue. Okay, so hopefully that makes sense, and I hope I didn't confuse you through that explanation. Again, if any of this was confusing, or if you didn't quite understand some of what I covered, please go back to the beginning of the recording